Hello, this is part 3 of aromaticity. Benzene is a nucleophile that reacts with an electrophile, forming a mono-substituted benzene compound. So we're going to talk about this and some of the reactions of benzene related to this. So why is benzene, as you can see here on the left, a nucleophile? Of course, it's due to the pi electrons above and below the plane of its ring. Therefore, it will react with an electrophile. Why? When it reacts with an electrophile, a carbocation intermediate is formed. In the second step of an electrophilic addition reaction, the carbocation reacts with the nucleophile, Z, to form an addition product. Now, because the aromatic product is more stable, down here you can see, the reaction proceeds as A, an electrophilic substitution reaction, rather than B, an electrophilic addition reaction. So we have the nucleophile, we have the electrophile, as you can see in Y. The first step forms a carbocation, and a nucleophile, Z, if it goes B, will form a non-aromatic compound if it's by electrophilic addition. If it goes, the second step goes to A and forms a more stable aromatic compound, then we have electrophilic substitution. Let's look at the reaction coordinate diagrams for these two reactions on the next slide. You can see on the left we have the reactants, on the right we have the products. The addition product is a much higher energy, not as stable, it's non-aromatic, as opposed to the substitution product, which is more stable and aromatic. And here in the middle you can see the carbocation intermediate. This diagram shows that the reaction of benzene to form a substituted benzene has a delta G close to 0. The reaction of benzene to form the much less stable non-aromatic addition product is at a much higher energy, so benzene undergoes electrophilic substitution reactions. Let's look at the general mechanism of electrophilic aromatic substitution of benzene. Because electrophilic substitution of benzene involves the reaction of an electrophile with an aromatic compound, it's called electrophilic aromatic substitution reaction. An electrophile substitutes for a hydrogen of an aromatic compound. That's actually what's happening. The first step, benzene is reacting with an electrophile, forming a carbocation intermediate, relatively a slow reaction. And in the second step, shown here, a base pulls off a proton from the carbocation intermediate, and the electrons that held the proton move into the ring to reestablish its aromaticity. This second step is fast and strongly exergonic. The proton is always removed from the carbon that has formed the new bond with the electrophile. Notice this proton right here is the one that is removed. So we have the first step, we have the second step, and we have a carbocation intermediate shown here in our diagram. Now let's look at a couple of the various reactions of benzene. 5 most common electrophilic aromatic substitution reactions are listed on this slide. Halogenation, bromine, chlorine, iodine substitution for a hydrogen. Nitration, there's a nitro group substituting for a hydrogen. Sulfonation, a sulfonic acid group substitutes for a hydrogen on the benzene ring. Fidel-Crafts acylation, an acyl group substitutes for a hydrogen. Fidel-Crafts alkylation, an alkyl group substitutes for a hydrogen. All of these reactions take place by the same two-step mechanism that we saw just on the previous slide. As we look at each of these reactions, we will notice that they differ only in how the electrophile is generated. Once the electrophile is formed, all 5 reactions follow the same two-step mechanism for electrophilic aromatic substitution. Let's look at halogenation on the next slide. The halogenation of benzene. The bromination or chlorination of benzene requires a Lewis acid, as you can see, such as ferric bromide or ferric chloride. A Lewis acid accepts a share and a pair of electrons. Now the mechanism of this reaction is shown on the next slide. The mechanism for the bromination of benzene. In the first step of the bromination reaction, bromine donates a lone pair of electrons to the Lewis acid. This weakens the bromine-bromine bond, thereby providing the electrophile that's necessary for electrophilic aromatic substitution. So we have the nucleophile, we have the electrophile, we have a carbocation intermediate formed, and any base in the reaction mixture can remove a proton, forming our product. Let's look at the mechanism of ionization. The electrophilic iodine is obtained by treating molecular iodine, as you can see here, with an oxidizing agent such as nitric acid. Once the electrophile is formed, iodination of benzene occurs by the same mechanism as bromination and chlorination. We have the first step and we have the second step. And again, any base in the reaction mixture can remove the proton, forming the product. The last slide we want to look at is the nitration of benzene. The nitration of benzene with nitric acid requires sulfuric acid as a catalyst, and here's sulfuric acid. To generate the necessary electrophile, sulfuric acid protonates nitric acid. Loss of water from protonated nitric acid forms a nitronium ion, the electrophile that's required for nitration. Any base present in the reaction mixture can remove the proton in the second step of the aromatic substitution reaction. So up here, the first reaction series we see is the formation of the nitronium ion, which is the electrophile. Here's our catalyst, and of course here's nitric acid. And now we have benzene functioning as the nucleophile. Here's our nitronium ion, our electrophile, forming the reaction that will give an intermediate, and then we have the formation of our product. That concludes the third part of aromaticity.